Ciao Liam, episode 2 of 6. The break your own build loop is 4 steps, always in this order. Predict what the instrument will find before you run it. Run the instrument as the chapter defines it on your own work, not on a toy example. Report what it exposed, especially the unwelcome finding, because that is the finding. Note the fix and the residual risk that remains after the fix. That loop is the assignment, and the instrument for this episode is calibration. Calibration asks one question: does the confidence your build reports mean anything? If your model says 90% confident on a prediction, does that prediction come true 90% of the time, or is that number a number you attached without testing it? Most builds never ask. This one will. Every prediction in your build needs a stated confidence, a number, not just a label. If your build does not produce confidence scores, you are not done with the build. Once you have confidence scores, here's how the reliability diagram works. Bin the predictions into 10 bins by their stated confidence. The 0-10% bin, the 10-20% bin, all the way to the 90-100% bin. For each bin, compute the fraction of predictions in that bin that were actually correct, the fraction positive. Plot fraction positive on the vertical axis against the mean confidence of the bin on the horizontal axis. A perfectly calibrated model lies on the diagonal. If the model said 80% confident, 80% of those predictions came true. A bar sitting above the diagonal means the model is underconfident in that bin. It was more right than it claimed. A bar sitting below the diagonal means the model is overconfident. It was less right than it claimed. The overconfident tail is the usual finding. That is not a coincidence. Training loss rewards the model for matching labels, not for being honest about uncertainty. The reliability diagram is how you see that. 3 numbers to compute alongside the diagram. The Breyer score, the mean squared error of the probability estimates. Lower is better. It summarizes the calibration in a single number without telling you where the error lies. That is what the diagram is for. The expected calibration error, or S, the weighted average of the calibration error across all bins. Weight each bin by how many predictions fell in it. A smaller ECE means the model's confidence tracks its accuracy more closely. ECE tells you magnitude, the diagram tells you shape. Temperature scaling: if your model is overconfident, and most are, you can divide the logits by a temperature parameter T greater than 1 to soften the confidence outputs. You fit T on a held-out validation set, then replot. T is a single scalar. It shifts the whole distribution without retraining. The critical trap: a good in-sample calibration curve is not evidence of good calibration. Replot on a shifted slice, a different time window, a different demographic, a subgroup the training set underrepresented. Report what moved. The in-sample result goes in the report for completeness. The shifted distribution result is the finding. 2 classical moves that turn the calibration numbers into questions worth asking. Descartes inward: how could my 90% confident prediction be false? What would a systematic deceiver have done to my training data to produce overconfidence in exactly that bin? This is not skepticism as philosophy, it is a specific diagnostic question. If you imagine a deceiver who contaminated your training data with label noise concentrated in the high confidence region, you know exactly which slice to replot. Hume inward: is the ECE I computed a fact about the world, or only a fact about my sample? What population is my reliability diagram actually characterizing? If the diagram was computed on the population that happened to appear in my data window, and my data window was not representative, then the curve describes a historical accident, not the deployment environment. These 2 questions together produce the shifted distribution replot. Descartes identifies the bin where contamination is most plausible. Hume identifies the population the diagram is not characterizing. Together they define the slice you need to test. The replot is not extra work, it is the answer to both questions at once. Loop report for the calibration instrument has 4 fields, all required. Field 1, the dated prediction lock. This is what you wrote before you ran anything. Include it verbatim, do not rewrite it to match what you found. Field 2, the method. Reliability diagram, computed how on what data. ECE and Breyer computed from how many predictions. Temperature scaling, T-value fitted on what held out set. Shifted replot on what slice and why that slice. Field 3, the result. The unwelcome finding goes here explicitly, not the model performed reasonably. The overconfident tail, if there was one. The ECE before and after temperature scaling, what moved on the shifted replot and by how much. If the shift was large, that is the finding, it means your calibration was population specific, not general. Field 4, the fix applied and the residual risk that remains after the fix. Every calibration fix leaves something. Temperature scaling softens the whole distribution but cannot fix calibration that varies by subgroup. That residual risk goes in field 4. Naming what you could not close is not a weakness. It is the honest report of a build you understood well enough to know its limits. Verdict for break your own build, the loop in calibration. The loop: predict before running, run the instrument, report the unwelcome finding, name the fix and the residual risk. The calibration instrument: reliability diagram on your own predictions, binned, plotted, compared to the diagonal. ECE and Breyer computed, temperature scaling applied with a held-out T, then replotted. Descartes and Hume are the two questions that drive the shifted distribution replot. Descartes names the suspect bin, Hume names the population the diagram is not characterizing. The shifted replot is the finding, not the ensample result. Loop report has 4 fields: dated, prediction lock, verbatim, method, result including the unwelcome finding, fix, and residual risk. No mistakes found is graded as not looking. Your turn, here is the prompt. The prompt reads, I have a artifact type, for example, a logistic regression classifier for loan default prediction that produces confidence scores. Here are 10 sample predictions with their confidence scores. List 10 predictions, each with the predicted label and the stated confidence as a decimal between 0 and 1. Here is a sample of my binned results. Paste or describe what you have for each bin you have data for. Give the bin range, the number of predictions in that bin, and the fraction that were actually correct. Help me compute ECE from these bins. Give me the formula, the per bin calibration error, and the weighted sum. Then tell me what shifted distribution replot I should run given that my training data came from describe your data source and time window. For example, loan applications from January 2022 to December 2023 from a single regional lender. Be specific about what slice to test and why that slice is the right one to expose population-specific calibration error. After you get the ECE and the replot prescription, run both. Compute the ECE yourself. Do not report Claude's number as your result without verifying it on your actual data. The replot result, not the ensample result, is the one to put in your instrument report. Break your own build, the loop plus calibration. Lay 'em in for bear.